Good to see everybody. Last week when we were together, we spent all of our time talking about ways that you could get molecules to stick to one another to form molecular liquids or even possibly solids. And primarily, we talked about nonpolar molecules and how they tend to stick together through something called London dispersion forces. London dispersion forces, they are just one type of intermolecular force, and in fact tend to be the weakest of the types that we are going to discuss. Today's video, we're going to look at the next level up. Molecules that stick together through forces known as dipole-dipole interactions. These types of interactions are limited only to polar molecules. You only see them in polar molecules. So on the first slide that we're looking at right now, we have two molecules, and we can compare them in a couple of ways. If you were to count the total number of electrons for each one of them, the first one on the left-hand side, H2CO, has a total of, let's see, one electron for each hydrogen. There are 6 electrons total in an oxygen and 8 in 6 total in a carbon and 8 in an oxygen. So you add those up and you get 16 total electrons. The second molecule, which is called ethane, C2H6, has, again, 6 electrons for each one of the carbons. That's 12. And another 6 electrons, 1 for each of the hydrogens. So this has a total of 18 electrons. So really similar total electron count between the two molecules. Additionally, we could look at something like molar mass. If I count up the molar mass of H2CO, it's right at 30 grams per mole. And if I do the same thing for the ethane, it's also about 30 grams per mole. And so if London dispersion forces were the only thing that mattered, you would suppose that both of these will have roughly the same exact boiling point. It should be a similar effort or energy needed to break apart those London dispersion forces. But we're going to find out in a minute that they don't, that one has a much greater boiling point than the other. So what are their differences? Well, C2H6, you can tell just by looking at the Lewis structure, is a very symmetrical molecule. And we know that symmetrical molecules tend to be nonpolar. So we have this nonpolar molecule, and we know that that means that the only type of intermolecular force that's going to be present in a molecule like this is the London dispersion forces, where electrons congregate on one side of the molecule, making it temporarily polar. Okay? On the other hand, if I look at H2CO, and I'm, in a true Lewis structure, we should put these lone pairs on the oxygen. Doesn't matter much. The big thing that I want you to take away from looking at H2CO is that it's asymmetrical. I could cut it through this carbon and hydrogen, and it's not the same on each side. I could also cut it through this side or through that carbon and hydrogen, and it's not symmetrical. And we know that non-symmetrical or asymmetrical molecules are polar in nature. Okay, so this is a polar molecule. Well, one of the things that we need to know about what that really means, to say something is polar, means that it has a permanent, not temporary, but a permanent partial negative charge on one side of the molecule and a permanent partial positive charge on the other side. And in determining how do you decide which side is going to be negative or positive, you really need to look at electronegativity. So usually this is what I do. I get a periodic table out. I look for the element that is furthest to the upper right-hand corner, closest to the upper right-hand corner. And that element is the most electronegative. Means it's best at pulling electrons to itself. And so in this case, oxygen is the most electronegative element. And because of that, we would say the partial negative charge resides on that side of the oxygen, and that the partial positive charge resides elsewhere. I usually just say it resides near the other atoms. And so we would say in this case that it resides near the two H's and the carbon. Okay? This is permanent. Whereas with the nonpolar C2H6 molecule, you can get LDFs, but remember those are temporary and therefore pretty weak. Okay? Now, I should also say before we move on that even polar molecules experience LDFs. Okay? They do too. And we would say that these two molecules should have pretty similar LDFs. But the additional attractive forces that exist between H2CO molecules outweigh the LDFs that either molecule experience. So the important type of intermolecular force is what's known as a dipole-dipole force. Okay? And we saw that word last week, dipole, but I want to reiterate what it means. Dipole is essentially saying that one side of the molecule is negative and one side is positive. And so for polar molecules, they always have that, and it's permanent. So what's a dipole-dipole force? Well, if I look here, you're going to note that this looks very similar to the drawings that we made of London dispersion forces, where we have two molecules, they're lined up such that the positive side of one molecule interacts with the negative side of the other molecule. And that interaction right here, let me draw an arrow. That interaction right there is what's known as the dipole-dipole interaction, okay? And it looks just like the London dispersion forces that we saw last week in those interactions. But what we have to remember is that this is permanent, not temporary, and therefore it's typically much, much stronger. The other thing I want to address before moving on is that in this particular diagram, I'm only showing two molecules just so we can look at the details. But I think it's important to remember that in a sample of any substance, you would be talking about trillions and trillions upon trillions of molecules. And they would all be lining up with their positive ends towards the negative ends of a separate molecule. So while we only show two molecules, the truth is it's going on in countless numbers of molecules that make up a particular sample. Okay, so finally in this video, let's go back to what we said at the beginning. We said these two molecules have the same molar mass. These two molecules have almost identical numbers of total electrons. But if I look specifically at their boiling points, I notice that there's a major difference here, okay? And remember that boiling means that we're going from the liquid to the gas phase, and that in order to do that, you have to break intermolecular forces. For formaldehyde, that happens at negative 19.5 degrees Celsius. Okay. Now, to be clear, that is not a very high temperature, but compare that to the ethane, which boils at negative 88 degrees Celsius. What should we take away from that? It's much easier to boil ethane than it is to boil H2CO, which is called formaldehyde. If it's much easier, that means the forces that hold the ethane molecules to one another must be weaker. And they are, because London dispersion forces are always going to be weaker than dipole-dipole forces if the molecules are close to each other in size. Okay, that's it for this video. We'll get back together soon. Take care.